Good afternoon and good morning, everyone. My name is Magdalena Marszałek and I am in technical sales at Zurich Instruments. Today, I will be your host during the Zurich Instruments webinar devoted to one of the hottest and most rapidly developing fields of science, quantum computing. In the next hour, our resident expert, Tobias Stille, will talk about the best approaches on controlling qubits in a fast and a scalable way. His presentation will consist of two parts, addressing first the creation of a Ramsey sequence live, and then discussing the concepts on how to control more and more qubits. Actually, after all this, there is also a third part where we really count on your engagement, the Q&A session. We will be answering your questions that you can submit throughout the duration of the whole event. You can start even now. And how to do it? Please use the Q&A tab and just type in your question, anytime. All right, please allow me to start with painting a little bit of a quantum landscape before Tobias will take you to the essence of this meeting. For quantum computing, we need different elements that together form a quantum stack. Here we display it in a simplified way. The foundation of the stack is a quantum device, here held by Christian from the ETH. Quantum processor. This is exactly where the magic happens. And now let's jump to the top. Application software, which could be compared to an outer shell that is going to be used by most of the customers, who are people interested in using the calculating power of the quantum computers in their own applications. These applications can vary greatly, but the essential part is to create algorithms that can translate the real-world problems so that they can be communicated to the working qubits. Additionally, knowing the type of the qubit and its flavor is beneficial for creating the most effective algorithms. Now, we want to connect the qubits with the algorithms. We have the hardware, kept at the temperature of tens of millikelvins. We have the software, and between them there is the interface, which is exactly where you can find Zurich Instruments. We have arbitrary waveform generators, quantum analyzers, and PQSC. This quantum stack in the picture is built at ETH in the group of Professor Andreas Wallraff, and it can control 20 qubits. Controlling qubits requires analog signals. On one hand, there is a signal generation, accurate and precisely timed. On the other hand, there is a signal readout, where the sensitivity and the speed of feedback to the algorithm is of a paramount importance. Zurich Instruments provide it all and much more. I guess everybody is excited now to find out how to put our instruments to the best use in quantum computing and learn how to control multiple qubits. Time to ask the first question to our expert. Tobias, would you please tell us a little bit more about the complexity of multiple qubits?
So thank you, Magda, for this nice introduction, and also welcome from my side. Let's dive directly into this main topic of this webinar. And as Magda said already, this stack can control roughly 20 qubits, which doesn't sound like much, but we see an exponential growth in qubit numbers of the systems of our customers, and we're indeed committed to scale with them. For example, consider the Open SuperQ, which is funded by the European Union, and where we committed to be able to control 100 qubits by the end of next year. So being able to scale the control instrumentation up for this number of qubits is challenging. However, it's not the only dimension in which is growing and scaling. So there's a second dimension, and this is the complexity of the algorithms and sequences. This is even true for a single instrument or for a single qubit. So for example, consider a typical sequence. About 10 years ago, it consisted of 2 pulses. Nowadays, we have typically hundreds or thousands of pulses that all need to be individually tuned up and controlled. And this is exactly the problem. So you cannot think about actually scaling your system size up to hundreds of qubits if you don't have the control over your waveform complexity. And that's exactly the part or the segmentation of this webinar. So in the first part, we will understand and discuss how we get a handle on this complexity. We call this the fast approach. Why is this the case? since when the complexity is handled, it's easy to get a first control over your system in a few hours. And programmable sequences, for example, like a Rabi sequence, it should be possible in minutes, and that's something which we will see. In the next part, we will discuss how we scale the number of qubits, and this is the scalable approach. And the highlight there will be that we show you for the very first time and our latest innovation. It will be a very new instrument, which, believe me, is something you haven't seen so far on the market. And in the end, of course, there will be a question and answer session, as Magda said already. So let's just dive directly into the part one. So how do we get a handle on the complexity? So for this, let's consider the simplest qubit control system that is possible, an arbitrary waveform generator and a quantum analyzer, which has essentially one job to do, and this can do it very well, which is multiplexed real-time readout of qubits. So what are the key tasks that these instruments need to be able to do, imposed by the quantum system itself? With our quantum computing control system, which we discussed today, we can control superconducting and spin qubits, which you see here in the bottom, very well and optimally. Why is this the case? Both of them use similar pulses for their qubit control. On the one hand, these are microwave pulses, for example, on the order of 6 gigahertz for superconducting qubits, or for up to 20 gigahertz for spin qubits. On the other hand, they also need very fast DC pulses with bandwidths of a few hundred megahertz. Flux pulses, for example, in superconducting qubits, are used for entangling 2 qubits and doing 2 qubit gates. For readout, both of these systems can be coupled to readout resonators or microwave resonators that change their frequency according to the qubit states. Spin qubits, in addition, have the chance to use a charge sensor to do a state readout depending on a transport measurement. But let's focus on now how our instruments can manipulate these qubits and how we can generate these pulses in a sustainable manner. And for this, we will have a look at our HDAWG, our arbitrary waveform generator, and we will discuss really the main topic or the main task that it has to do, which is playing many and high fidelity gates. And this has essentially two components. On the one hand, we really need great hardware to really reach these high fidelity gates. On the other hand, we need to reduce the memory and the complexity of our waveforms and and sequences to be able to play many gates. So, and what is the best way to actually explain this, or what's the nicest way, which we all enjoy? This is looking at a nice result from the field. And here we discussed the example of IBM, which used one of our AWGs to make record short single qubit gates for superconducting circuits and with highest fidelity. In the end, they achieved 4 nanosecond gates time within a fidelity of above 99.7%. How did they do this? They essentially took the typical pulse shape, made it shorter, and then discretized it, really using these roughly 400 picosecond time resolution that our AWG gives. And this gave them enough flexibility to be able to change these step heights in an optimal control algorithm and try to minimize, with every shape change, the excitation of unwanted states which were close by. And what you need to understand, of course, or acknowledge is that, okay, if you want to see whether your qubit changed on the 0.1% level, or your gate fidelity changed on the 0.1% level, then you need to play 1,000 pulses to see a first effect that you see it's dropping in fidelity. So this really required to play several thousands of pulses with the timing accuracy and the resolution being stable for hours. And this is essentially what we could provide with our instrument. So this really shows you the importance of providing optimal hard specifications with the instruments, such as the sampling rate or the vertical resolution, which then give the researchers enough flexibility to optimize their pulses. But that's not the full story. In the end, it's a really great result, landmark method essentially for gate optimization. However, being in close contact with our customers, we identified that our instrument needed further improvements to really be making this a scalable technique. Why is this the case? Well, as you see here in this plot, most of the experiment cycle went actually into uploading and initializing the instrument and also data processing. And the actual measurement time on the qubit chip was almost negligible with respect to these other two. So what we really needed to make sure is we needed to increase the scalability by removing the main reason for this long upload time, which is that there was a lot of redundant information needed to be uploaded to the instrument. So what we developed recently is that we can now play more than 16,000 pulses with a technique called gate-level sequencing, which essentially means that you really only upload the minimal amount of information to your system. And how does this work? Let's have a look at a simple sequence. Let's use a Ramsey sequence, 2 pulses, and one of the first things which you realize, and I think everyone will understand, is that you don't want to store zeros. So if there's no pulse being played, you don't want to fill your memory with zeros that it needs to play. So you rather tell your instrument, okay, just solve, don't output anything, but you don't play zeros. Okay. Then you also want to, of course, only upload a waveform once, a shape, a pulse envelope, for example, a Gaussian, and want to reuse it again. And the main thing where typical sequences waves, pulses in a sequence do differ is the center frequency and the phase and the amplitude. So actually what you want to do is you want to tell the instrument, okay, play at that point a Gaussian pulse with a certain frequency and phase, and at a later time change the amplitude and the phase, but maybe play the same frequency. And how does this work actually in our instruments? Let's directly have a look at our first example. And for this, what we will do is we will connect the outputs of our arbitrary waveform generator to the oscilloscope, which is included anyway in our quantum analyzer. And we will use this oscilloscope to have a look at the output of the AWG. Good, so now in the upper part of your screen, you should see now the live stream of our quantum computing control system. And as just mentioned, we will use this AWG and to monitor this, or to write this Ramsey sequence. And we will monitor the 2 outputs, which you will see here, using the oscilloscope, which is in this quantum analyzer. We also have connected a trigger cable just to be able to trigger the result acquisition. So and with this now, let's go right into how do we control these instruments. Okay, so what you see here is our Lab 1 graphical user interface that can be used to control the instruments. Of course, everything which we do here can also be controlled by using our APIs through Python, LabVIEW, C, or .NET. What you see here on the left are the different functionalities. Currently, we are connected to the oscilloscope of the quantum analyzer. And you see here the different tabs, for example, the scope tab. And which, if you click on these, then these open here and you see the additional functionality. Of course, you can connect several instruments together. So what we have here connected now and opened is from the AWG, the sequencer tab. This is where we write our AWG program. And we also have the output connected, in which we can control the voltage range and whether it should output something or not. In the bottom, we have the oscilloscope visible from this quantum analyzer, and this is where we'll use which we'll use to display our results. Good, so let's start with writing our Ramsey sequence. So first we define a waveform. Let's do a Gaussian waveform, and for this we use just a predefined snippet, which we have of a sample length of 320 samples. We tell this Gaussian to be at the maximum amplitude and center it within this waveform at 160 samples. And the width, let's say it's just 50 samples. All of these samples, of course, are on the full sampling rate of the system, so at 2.4 gigasamples. And of course, you can upload your own predefined waveform if you don't want to, of course, use a Gaussian or so. So now now we want to play this Gaussian waveform on both channels. So this we do with the play wave statement. And for this play wave statement, we just write for the first channel and for the second channel this waveform in there. Then we tell the instrument that it should wait until this until this this waveform is finished, and then we say we want to have it to wait for 10 samples. This is actually telling the instrument or the FPGA to stall. This runs at a different clock of about 3.3 nanoseconds per sample. So now to make a waveform, to make a Ramsey sequence, what we need to do is we need to just repeat this. So we play a second pulse here, and in this case we do just for fun have it on half the amplitude. So we just play it on half the amplitude, so at 0.5 times. And then in the end we want to send out a trigger, and this we do by just setting the trigger output to 1, give it a certain length, again of 33 nanoseconds, and then in the end we set the trigger to 0 again. And with this we've written a simple Ramsey sequence within roughly 2 minutes. Good, so now we compiled this sequence onto our AWG, and it worked well. The compiler tells us it's green, and now we just run it. And if we run it, so the first thing which you see on the oscilloscope are indeed these 2 pulses, and you also see the trigger here that on which we triggered currently the oscilloscope. So now, of course, we can also have a look at the second output. So we just choose here the second input. We make sure that they're both on the same level, and then we just run it again. And indeed, you see that these 2 pulses are overlapping, and we see the 2 output pulses here. So now let's make the situation a bit more interesting. Good, so now we programmed a simple Ramsey sequence with 2 Gaussian pulses, but there's one key ingredient missing, and that's the frequency. Especially for microwave pulses, we often use IQ up conversion to convert a pulse at an intermediate frequency of, say, 100 megahertz to microwave frequencies at, for example, 6 gigahertz using a local oscillator. That way, we gain control over the phase, frequency, and the amplitude. For this, what we need to generate are 2 pulses with a phase difference of about 90 degrees and a frequency of 100 megahertz. What are our options? On the one hand, of course, you can just use or do what we did so far. You can just program the frequency sample by sample into your IWG. However, that's not very memory efficient, again, because you upload a lot of redundant information. What is better is to actually use an internal oscillator which runs completely in parallel to your AWG sequence and doesn't consume any memory, but you still have the full control over the phase and the frequency of this internal oscillator. And what we can do now is we can just multiply this sinusoidal signal at the output of our AWG, and we just multiply these 2 outputs, and then what we get is a nice AWG defined envelope with a specific frequency and phase. And how does this work in the actual experiment? Let's go back to our simple Ramsey sequence and directly have a look at how we do this in lab 1. Good, so now how do we enable now for this simple Ramsey sequence the center frequencies? So for this we go to the output, and this is exactly what you saw before. We have here the oscillators where we define our frequency. These get here assigned to a sine generators. We will use the first 2 sine generators, and we will tell these 2 sine generators to be 90 degrees out of phase. And now we multiply the sinusoidal signals to the output of the sequencer just by enabling this button here. And then if we run the sequencer, what you see is that indeed these 2 pulses get modulated by the frequency that we want. And now what we can do is we can actually, let's zoom in a bit and have a look. And what you can see is that indeed these 2 frequencies on the 2 outputs are indeed 90 degrees out of phase. And again, the important thing is to mention that all of these settings here on the oscillators and sine generators can be controlled also in real time using the AWG sequencer by enabling this button. So now we have seen how pulse level sequencing works for microwave pulses. And the question is now, does this easily extend to also these DC pulses? And the answer is unfortunately no. Why is this the case? pulses around DC that are needed for 2-qubit gates, for example, flux pulses for superconducting circuits, they distort on their path from the AWG down to the qubit because they go through different filters, for example. And this limits the gate fidelity, as can be seen here in a paper from Leo Di Carlo, where he used such a flux pulse to exchange an excitation between 2 qubits. And what you can see is from the 70 to 80% contrast is that the fidelity is limited in that case. And also these oscillations are, this chevron type pattern is distorted to one side. And and there's an additional problem, and the problem is that because these pulses have long transients, then the optimal pulse shape actually depends on the pulse history. So if you played several pulses before or not. And this means pulses cannot be reused, and also the feedback is not possible. Okay, so what Leo now achieved is a real-time precompensation of this pulse, resulting in a nice and symmetric 2-qubit gate that worked with much better fidelity on the order of about 90%. Again, essentially a great result. So what was our contribution to this? We provided at the output of our AWG real-time precompensation filters, which means that we implemented a set of filters that pre-distort the pulses for you. And of course, it's still a hard problem to characterize the distortions in your cryostat, but as soon as you know it, you can just program these filters, and the result is that you get what you program, meaning you can always rely that what you program into your AWG will actually arrive at the qubit. And this really helps you to, on the one hand, reuse pulses again, and also again minimize. And this means minimizing the information that you need to program on the way, and you can do feedback. Good. So this was the part of the AWG. We saw how we can really optimize our gates and the number of gates in terms of fidelity and number with optimized hardware and this pulse level sequencing, or this reduced memory and bandwidth complexity that we need to upload to the device. So now let's have a look at our quantum analyzer and see how we can actually read out the states of these qubits. And the way that you typically do this is to measure superconducting or spin qubits with a resonator, is you determine the resonance frequency of a resonator that is dispersively coupled to the qubit. This is typically done with a probe tone, which you see here in blue. And if the transmission of this probe tone is high, in this case the resonator sits at this place and the qubit is in the excited state. If the transmission is low, the qubit is in the ground state. So now, to save control lines that need to go into your cryostat to the qubit chip, people typically frequency multiplex these readouts. Okay, this means that they take several resonators at different frequencies, which are all coupled to a specific qubit, and then they read them out all at the same time by just sending several tones at the same time down, which each of these probes, each of these tones then probes a separate resonator. And this, let's have a look again at a few results from the field. The first one is Leo Di Carlo, and he used our instrument to really be able to measure the quantum efficiency of this dispersive readout and really characterize different influences of noise, and also make sure that he can do the optimal readout using integrated weights. On the other hand, there's Andreas Wallraff, who took this signal-to-noise maximization to a maximum and read out 5 qubits in parallel, and with very short readout pulses on the order of 18 nanoseconds. And he could still do an assignment fidelity of the different qubit states of this multiplexed readout to on the order of 97%. Good. So how did we help in both cases? Well, we provided, even actually developed with the researchers the UHFQA, which is really a high-performance instrument that has only one job, which can do this real-time readout of this multiplex qubit using a real-time analysis chain. And how does this this essentially helps you to maximize the signal to noise for each qubit readout. And this is how, in the end, allowed the researchers to not use their own FPGAs, which they had to program, and it also helped them reduce the amount of data and the upload time which needed to be transferred either to the system or to the computer. Good. So how does this workflow goes into the UHFQA? You start initially with digitizing the signal that consists of all the frequencies of your readout signals, and then you apply. And then this instrument applies a matched filter, and this matched filter is essentially an integration with a weight which is matched to the response of the specific qubit that you would like to read out. And this really helps you to select the contribution only from the target qubit and to remove the influence in your signal processing of all the other qubits. Okay, so what happens then if you look then at the result in the complex plane is typically that you see several dots or clouds which all correspond to results of the qubit being the excited and the ground state. And what you want to do now, you want to distinguish between these two states in real time. And for this, you have to modify these results and clean it up such that you can put a nice threshold. And the way that the UHFQA does this is it first rotates the signals onto one quadrature, and then in the end, it does a crosstalk suppression operation, which really removes all the remaining influences of all the other qubits. And in the end, what you get are two nice clouds of data. One of them corresponds to a qubit in the excited state, the other one in the ground state. And you can place a very nice threshold on this quadrature. In this case, it is the I quadrature. And say, okay, if the quadrature is higher or lower than a certain state, the qubit is in the excited and the ground state. And this can be done in parallel for all the 10 qubits and then send out in real time to this digital input-output port. And all of this takes about 240 nanoseconds after your last sample is in, and we are continuously improving on this. And we are not only improving on this latency, but we are continuously also improving this workflow. For example, just recently, we launched a new digitizer option on this instrument. So if you're interested, just check out our website. So with this, we come to the end of the first part. So, before we go to the next part, we ask the question, okay, why can we claim Rabi oscillations in a day? And the take-home message in this part is, okay, we've shown how we can reach better gate performances by really pushing the performance of the basic or the hard specs of the instruments to the limit. And on the other hand, do this gate level sequencing both for microwave, but also for 2-qubit gates, for example, with this real-time precompensation. And that way, get really a handle on this complexity. So this really helps you to speed up writing your manipulation sequences. And with this good and efficient workflow of the readout, you can really optimize and get your results out fast. So all of this taken together, it really gives you the benefit of a short time to experiment. And this is why we typically comfortably claim that if one of our application scientists visits your lab with our instruments and connects the instruments to your cryostat or to your quantum computer, that within a day, typically faster, even with half a day, you can you can see Rabi and Ramsey oscillations on your qubits. And with this, we end the first part, and I'll give back to Magda.
Tobias, thank you very much for the demonstration in the first part. Before we move on, I would like to remind you, comfortably seated in front of your screen, that you can submit any question you might already have on the topic via the Q&A tab in the bottom of your screen. Okay, Tobias, so now you are ready to take us on the journey where we will see how to take the scalability of qubits to the next level. And, as you mentioned before, there is some exciting news that you would want to share for the first time today, exclusively with our audience. We can't wait. Tobias, the screen is yours.
So, thank you, Magda, for this, and let's jump right into the next part where we discuss how we scale our system to 100 qubits and more. And one of the key challenges which need to be accomplished is that one needs to design this quantum computing control system in a way that it's greater than the sum of its parts. What do you need for this? You need, on the one hand, one controller which interfaces and synchronizes all the instruments. On the other hand, you need to address the challenge of exploding system complexity. Many instruments are needed in addition to these control instruments and also cabling, and this is something you need to reduce. And this is also the part which we'll discuss first now. And what you can see is typically that even the big companies, they show you their nice cryostats, Google here, for example, but what they typically don't show you is all the control instrumentation which is needed to operate their qubits in this cryostat. And even here, for a few tens of qubits, you see that you need a lot of different instruments and cables. And this works fine for a few qubits, but if you want to scale this to hundreds or even thousands of qubits, that's something that just doesn't scale in your favor. So what are the options here? So let's consider first now again our simple system which we had before, an HDAWG and a UHFQA. And what you can see here in the sketch is that you need to actually operate and control the qubits, additional instrumentation, especially for frequency up and down conversion, or for example in the readout line, you need circuits to generate and maybe even cancel out pump tones for your parametric amplifiers. And these additional instruments, for example, mixers or local oscillators, to reduce this complexity in this case and the tune-up of them, there's two approaches. And the approach that we chose for the up conversion, and especially in combination with our HDAWG, is to combine these instruments in a new instrument or in a new box, which really simplifies the cabling. And in this case, we can do up conversion of up to 4 microwave channels using an 8-channel HDAWG. However, if you think about now the signal quality which is needed for the UHFQA, this approach is not as simple. And what we did in this case is we actually decided to combine everything into one instrument. And this is the super high frequency quantum analyzer. And it's really now this new innovation which we will show you now. And and I hope that I can excite you as much as we are here at Zurich Instruments to really show you that this is really the next generation of quantum analyzers. So let's have a look at this instrument. And here is our newest innovation. Believe me if I tell you that this is truly an instrument unlike any other commercially available quantum control device that you've seen on the market. First of all, it features 4 readout channels. Each channel can read out up to 16 qubits or 8 qubits. This corresponds to 64 qubits or 32 qubits for the full instrument. Next, each channel has the up and down conversion integrated up to 8.5 GHz. Importantly, we use an up conversion technique that is broadband, clean, and does not drift. This is in contrast to the normally used IQ up and down conversion technique. So with this instrument, from the first turn on, you will get a stable and clean signal, both in the signal generation, but also in the signal acquisition. Of course, each channel has the same well-established workflow included that helps you optimize your signal-to-noise ratio for each qubit that we also know from the UHFQA. The instrument itself comes in different configurations, such that also small systems with a few qubits can profit from it. Especially, we will have a version which only features 2 readout channels. What is important to remember is that for a standard readout, with this instrument, no other instrumentation is needed, except the cryostat, the cold amplifiers, and your quantum chip. This means you can directly connect the input and the output of this instrument to your cryostat. So I hope you got as excited as I am, and if you are as excited, then I would ask you to sign up at this link, which we'll show you at the bottom of the page. And this link will actually provide you to a form where you can sign up for our webinar, which will be in October and which will be only focusing and demonstrating performance of this instrument. And the official launch of this instrument will be in roughly a week on September 1st. And this means we will actually publish it on our website and you get the first information there. Good, so I hope I could convince you now that we are really on the right track to be able to scale our system to be able to control hundreds of qubits by strongly reducing system complexity and maximal integration into a single instrument. So let's focus now on the remaining task. How do we combine all the instruments into one system? And for this, we choose a central controller, the programmable quantum system controller, and we choose it in a star topology. And why we choose this configuration? Well, the star topology is scalable and high performant. For example, it allows to synchronize all instruments to sub-nanosecond precision. In our case, this means we can synchronize 18 instruments or 144 AWG channels to about 200 or 400 picoseconds resolution. In addition, there is the single link between the one AWG and the central controller really maximizes the data transfer rate between the instruments and helps to distribute the clock and the data to the full system without loss of performance. And that's really in a strong contrast, for example, if you go to a daisy chain topology where you add a jitter with every additional instrument that you have, and you reduce your bandwidth. So what is now really the key figure of such a system and really shows you how well such a system works and whether it has the potential to scale up to lots of qubits. And this is feedback. This is really the part which makes the QCCS bigger than its components. So why do we want feedback? On the one hand, feedback helps you to better prepare your initial states of your system. And this helps you to improve the fidelity of your algorithms and gives you relaxed constraints, for example, on the thermal occupation of your system. In addition, if your central controller is intelligent, it really enables you to do global quantum error correction. And this is really the key, or arguably the key element which you really need to do a large-scale working quantum computer where you can do, for example, surface code decoding on a global system level. In addition, ancillary reset really helps you to improve the performance of your algorithms, for example, by reduce the leakage in quantum error correction codes. So one of the key figures in this case is always the question, okay, how fast can we do this feedback and quantum error correction? And in our case, we distinguish between two types of feedback. On the one hand, we have the active reset, which is a local feedback where a qubit is read out and it's acted upon it essentially in a loop back to itself. On the other hand, we have the global feedback where essentially an arbitrary amount of quantum analyzers can send their results up to the central controller. This will decode the signal, and then it will send branching decisions to the different instruments. And then in that way, you can really make sure that an error which happens at some part of your system can be corrected maybe at a different part. And the active reset, we can typically do within 300 to 400 nanoseconds. The global feedback, which is really enabling the scaling up, we do it in currently less than 700 nanoseconds, but we're continuously improving on both of these figures. And especially this new SHFQA will also help a lot in that respect. Just to mention, there's of course success stories in this for feedback already achieved with our instruments. For example, Andreas Wallraff could stabilize a Bell state with 74% last year using this ancillary reset. Good. So now, before we end this webinar, let's have a look at the last live demo. And what we will do there is we will configure our quantum computing control system to do an active reset. And to do this active reset, just let's recapitulate quickly again what this means. So consider, for example, you have a moderate lifetime of a qubit of about 10 microseconds. You typically have to wait tens of microseconds until after an algorithm, your system is decayed to a ground state. And even then, thermal population can give you still a remaining excitation. So what you can do now is you can directly after an experiment run a single shot readout that determines the state of the qubit. And this result then gets communicated to an AWG. And this AWG then plays a pulse or not, depending on whether the qubit is in the excited state or not. And in this case, it can really bring down the excited state population of your qubit within very short time, 100 to nanoseconds to about a microseconds. It can really bring it down much faster than the natural lifetime of the qubit. In addition, you also get a better fidelity because you also remove thermal population to a certain extent. And this is now the example which we will have a look now at a live demo. And in this demo, what we will do is we will first simulate a qubit readout of actually 2 qubits using our quantum analyzer. This will be done in a loopback configuration. So we configure the AWG in this quantum analyzer to simulate this readout. It will be detected. And then the results of this readout will be sent through an AWG. And depending on the states of the qubit, the AWG will play either a rectangular pulse or a Gaussian pulse. And again, we will monitor all this output with an oscilloscope in another UHFQA. So let's jump right into this demo. Let's have a look again at the real instrumentation. And what we do first is we do the loop back connection of the quantum analyzer, which we will use for simulating the qubit readout. So we connect the output to the input 1 and the output 2 to the input 2. And then what we actually have already connected in the back is the digital input output, which will transfer the results of the qubits. But not now what we want to do is we just want to make sure that this quantum analyzer tells the AWG when the measurement is done. And this we do just by a simple trigger line outside. Of course, we could also use the digital input-output connector. Good. So with this, everything is set up. Let's have a look at the instruments again and the control. Good. So now here you see again our Lab 1 interface, and at the bottom you see the AWG sequencer of the unit which we'll use to simulate a qubit readout. And essentially the main part which you see here is we are having 2 frequencies, one at 100 megahertz, one at 150 megahertz, corresponding to 2 readout resonators. And what we will do in this repeat loop statement here is we will switch between being in a high amplitude and at a low amplitude, just simulating a qubit readout. So if you now run this, then what you can see here in the upper part, this is the quantum analyzer result. Here you see now in the IQ plane, you see actually for the first channel, you see 2 plops, this one here and this one here. And for the second qubit, you see this one here and this one here. So we do simulate now these 2 plops. Good. So now what we want to do is we want to do the real-time discrimination of these results for these 2 qubits. And what we do there is we first need to configure our analysis chain. And here we have the integration, we have the rotation, the crosstalk suppression, and in the end we have the threshold. And I already pre-configured the threshold to lie at 1 and minus 0.5 volt. And this, if you go back to this quantum analyzer result, you see these thresholds here, minus 1.5 for the second channel, plus 1 for the first channel, will nicely distinguish the 2 states. So now, how does our results look like at the end or after thresholding? And for this, we choose to look at this at the end of our analysis chain. And what we do in this simulation here is we actually have 100 samples or 100 repeated measurements in which the qubits alternatively change their result. So if we now run the sequence, then what you see is that we get an alternating sequence for these 2 channels. First, the qubit 1 is in the upper state, then goes down, and alternating for the other way. Good. So now we want to transfer these results in real time to the AWG. And we do this via our digital input-output connector, which we configure using this tab. And in this case, we say the mode is it should forward the quantum analyzer result, and it should forward it on these first 7 bits. Okay, and we will actually use the first 2 bits of this design. And now we go and look at the AWG. So this is now the different instrument. And here, this is a simple sequence which essentially just repeats or waits 100 times for a result. It waits for the trigger that it gets the OK from the quantum analyzer that the result is done, and then it will apply a simple switch case. And in the first case, that if the result is corresponds to the bit number 2 or the bit configuration number 2, then it will play 2 rectangles. In the other case, it will actually play a negative rectangle. Good. So now let's start the sequencer and have it wait for the results. And now we look again at our scope. This is again the other UHFQA, just for remembering, but essentially you can just see it as a scope, and we will look at the signal input and the trigger input of the signal. And now we just start our simulated measurement, and if we do this, you indeed see that we see an alternating sequence of pulses roughly every 25 microseconds, which is currently the time that we wait until the next readout is simulated. So you can see now this is really a simple setup where just to remind you again, this one here we do in the first quantum analyzer, we do a qubit readout, then we transfer these results through the DIO to our AWG, and then the AWG does a basic sequencer decision where it says, okay, in one configuration, it will play a pulse which goes down, in the other one, it will play a pulse which goes up. And with this, we finish the sequence and also the webinar. Let's go back to the slides.